Point 4, the logarithm function. Logarithm function. The logarithm function, the form of it is y is equal to log ax. This is read as y is the logarithm with a base of base a pen's not cooperating, a base a of x. There's a couple of definitions here. One is that a has to be greater than 0. A cannot equal to 1. And the domain all x such that x is greater than 0. Now we're going to discuss some attributes here. Y is equal to log base a of x This symbol means if and only if x equals to a to the power y. If no base is given, then we assume that the base is 10. If we're dealing with a natural log, y is equal to natural log of x if and only if x and the base is e to the power x. Remember that we previously defined the number e and found on your calculator. We're just taking an approximation here is 2.72. To change logarithm statements to exponential statements, which is necessary for many of the problems that we do, we use the principle y is equal to log base a of x if and only if x is equal to a to the power y. So given that log base 123m is equal to 3, if we rewrite this as an exponent, we get m is equal to 123 to the power 3. b is equal to natural log of 9 if and only if e to the power b is equal to 9. 4 equals to log base a of 24 if and only if a to the power 4 equals to 24. And then changing exponential statements to log statements. X is equal to a to the power y if and only if y is equal to log base a of x. For example, 4 is equal to a to the power 5 if and only if log base a4 is equal to 5. Now, we want to go ahead and speak about the domain of the log function. So, in our definition, we said that the domain of the log function must be greater than 0. If y is equal to log base a of x, the domain x must always be greater than 0. And that kind of follows because we cannot take the logarithm of a negative number, or 0 for that matter. So finding the domain, examples. Function given is f of x equals to log base 3 x minus 7. To find the domain, we would simply set x minus 7 greater than 0, so x has to be greater than 7. Domain, all x greater than 7. Or from 7 to infinity, not including 7. In other words, any number that is greater than 7 is going to be is going to result in us taking a positive logarithm. F of x equals to log base 5 x plus 2. Set x plus 2 greater than 0 x is greater than -2. Domain, all x greater than -2, or from -2 to infinity. Observe that, again, any number greater than -2 is going to result in a positive number in the parentheses, and we will be taking the logarithm of a positive number. F of x equals to log base 6, 4 minus x. Set 4 minus x greater than 0. So taking away 4 from both sides, we get x is greater than -4. And then dividing by -1, we get x is less than 4. Notice the flip and the sign because we divided or multiplied by a negative number. So the domain, all x, such that x is less than 4. So any number that is less than 4, because when we substitute it in here, when we substitute it into the equation, the function that we're given is going to result in a positive number. So this is from -infinity to 4. F of x equals to ln natural log x squared plus 6. Notice that in this case, the domain is all real numbers. Domain is all real numbers because if we were to try to make a substitution or set that greater than or equal to 0, we would have a quandary because no matter what value for x you substitute into this equation, into this function, the value in the parenthesis will always be positive. X squared plus 6 is always positive, even if x is a negative number and we square it, it becomes a positive number. One more example. F of x is equal to the natural log of a rational expression. So to do this, the critical number here is x cannot equal to 3, right? So set 3 here. Use a number line test, just like we did for rational testing rational functions. Say a number between -infinity and 3 would be x is equal to 0. And if we substitute into the function, we get f0 is equal to 1 over 0 minus 3, which is -1 over 3, which is a negative number. So this whole region is negative. Then if we substituted a number that's greater than 3, say x is equal to 4, we get f4 is equal to 1 minus 4 minus 3, which is equal to 1. So this whole region is positive. In other words, the solution, the domain, is from all numbers greater than 3, x greater than 3. Or from 3 to infinity. Find the domain of f of x equals to log base 5 of 1 plus x over 1 minus x. So we have an intercept. X-intercept is equal to, from the numerator, x-intercept by setting 1 plus x equal to 0. X is equal to -1. And then on the denominator, x cannot equal to a +1. So these are the critical points. Critical points on a number line. So we're going to make a number line, -infinity to -1 to +1 to infinity. And now the goal here is to check to see where the values are positive. So between -infinity to -1, we can test, say, x is equal to -2. So 1 minus 2 over 1 plus 2. This gives me a negative number, right? -1 over 3. So this whole region, this whole interval between -infinity to -1 is negative. That's not what we're looking for. We're looking for positive. Then between -1 to +1, we can, of course, test x is equal to, this should be -2 here. Easy to test x is equal to 0. So 1 plus 0 over 1 minus 0 is 1. So this region is positive. Then we test a number that's greater than 1, say x is equal to 2. So 1 plus 2 over 1 minus 2, which is a positive number. Oh, no, sorry, that's a negative number. We're dividing by negative, which is less than 0. So this is negative. So the domain is between -1 to +1, that interval. All x, such that x is between -1 and +1, or in the interval notation from -1 to +1. Okay? Remember, this interval is the region -1 to +1. This is the interval -infinity to -1. And this is the interval from 1 to +infinity. Now, I'm just briefly going to discuss the graph of the log function. So one, the log function is the inverse of the exponential function. Essentially what this means is that if we think about let's draw a couple of graphs here. Okay, so we've got y and x. And recall that the exponential function had the form where it did this and then did a steep increase. And the points -1 and 1 over a, 0 and 1, and +1 and a were on the graph. Now, in the log function, all we would need to do then is take inverse values. Instead of 0 and 1, we take 1 and 0. Instead of 1 and a, we take a and 1. And instead of 1 over -1 and 1 over a, we take 1 over a and -1. And that gives us the curve for the logarithm function. Think about domain and range here. Here the domain is negative to infinity to positive infinity, and the range, recall that the range was from 0 to infinity. In the logarithm graph, the domain and range are flipped around. So the domain is 0 to infinity, and the range negative to positive infinity. I wanted to graph this with the calculator and show you the inverse nature of it. Let's say we graphed y is equal to 2 to the power x. That's the exponential function. And then if we graph the logarithm function, log base, to get log base, you would have to press the map button and scroll down to log base. And then I'm going to type in base 2 of x. And graph it. And I want to put this in a square window. And then put in the reflection line, because these were inverses, so we're going to put in y is equal to x and graph it. And you can see how symmetrical the graphs are about the line y is equal to x. I'm going to capture both of these images and put them into the calculator. I'm sorry, into the notes. So this is what I graphed, and then the actual graph, I'm going to capture that as well. And place it into the notes so you can fool around with your calculator and see what's happening with the graphs. Okay, I just wanted to demonstrate the nature of the graph. The second attribute of the logarithm function is that the graph is smooth and continuous. And of course, I mentioned the domain. Domain is 0 to infinity, and the range is negative infinity to infinity. At this point, I'm not going to go over more attributes, but perhaps we can also mention that the graph contains the points. The inverse of the exponential function contains the points 1 and 0, because we mentioned this in the exponential function, so I wanted to relate it to this. A and 1 and 1 over a and negative 1. Now, to solve logarithm equations, by the way, this translations can be done with this type of graph also by moving left and right and up and down. As you can imagine, the x values and the y values would change based on the standards for transformations. I wanted to get into solving logarithm equations. Logarithmic equations. And we're going to do a lot of examples here. Here is question 1. Find the exact value of log base 6 of 36. The way to do this problem is you would set y is equal to log base 6 of 36 if and only if 6 to the power y is equal to 36. So 6 to the power y is equal to 6 squared. And since the bases are the same, we can go ahead and say that y is equal to 2. So the exact value of log base 6 of 36 is y is equal to 2. Solve log base 6 x is equal to 2. So all you need to do here is rewrite this as an exponent. X is equal to 6 to the power 2, which is equal to 36. Solve log base 2, 9x plus 9 is equal to 4. So we follow the process of rewriting as an exponent. This means that 9x plus 9 is equal to 2 to the power 4. So 9x plus 9 is equal to 16. So 9x is equal to 7. So x is equal to 7 over 9. Log base x of 81 is equal to 2. So in this case, x is the base. So keep in mind that the base to the power 2 must equal to 81. So x is equal to plus or minus the square root of 81, which is equal to negative 9 and positive 9. However, notice that if we checked the base based on our definition of the logarithm function, okay, going back to our definition here, I want to refer back to this to make sure you say that the base a has to be greater than 0 and cannot equal to 1. So we have to eliminate the negative base. We can't have a negative base with this. So we eliminate this one. So x is only equal to positive 9. Okay. Base of logarithm must be positive. So 4x is equal to 6. So we're going to rewrite this in the logarithm form. The logarithm form, remember that if y is equal to ln x, if and only if x is equal to e to the power y. So what this is saying is that 4x must equal to logarithm of 6. Okay, just rewriting 4 here is the y, so y must equal to 4. So e to the power y is equal to 6, so y is equal to the logarithm of 6. Dividing both sides by 4, x is equal to the logarithm of 6 divided by 4. More examples. E to the power 6x plus 7 is equal to 15. So rewriting as a logarithm, we have 6x plus 7 is equal to natural log 15. So 6x is equal to natural log 15 minus 7 x is equal to natural log of 15 minus 7 over, make sure that 15, that you're not taking the logarithm of 15 minus 7, but that you separate that 15 from the minus 7 divided by 6. By the way, you can actually put that in a calculator and get your answer, can't you? Logarithm, get an approx. This is called the exact answer, by the way. Exact answer. Exact answer. Because if you put it into a calculator, for example, if I put natural log 6 over 4 in the calculator, I would get an approximation. Natural log of 6 divide 4 would give me an approximation of 0.45. And if I were to take, say, natural log 15 minus 7 divided by 6, and then divide that answer by 6, I would get negative 0.715. So the approximation would be negative 0.715. Just to give you an idea of what the actual number is. One final example for this chapter, chapter 7, question 7, log base 3 of x squared plus 6 is equal to 4. So x squared plus 6 is equal to 3 to the power 4. So x squared plus 6 is equal to 81. So x squared is equal to 75. So this you can, sorry, this is plus, no, 75. What am I doing? Square root of 75, which is plus or minus 5 square root 3. So this is great. X can be negative as well as positive, because once we square it, it becomes a positive number. All right, let's go ahead and end this video.